this on in the back? Great. Sorry, Group H, I don't have fun walk-on music like the last group that just got started. I'm sorry about that. I'm not used to being the first one. So we've been doing some work in minimally invasive surgery, and we're just using minimally invasive surgery, or MIS, in order to be a tool for us to develop our invariant of distance to break. So what is minimally invasive surgery? It's very different from open surgery that has been used in the past where they completely open the body cavity. MIS is actually where they just make small incisions into the body and use tools instead of their hands to manipulate the organs inside. Now this brings several perceptual issues, such as a decrease in haptic force perception, simply because it's a mediated process through the tools. So this perception of tissue, what the surgeon is trying to do is have a material compliancy and understanding that material compliancy through dynamic touch on using these tools. So as the stiffness of the tissue is force increases into that tissue, the stiffness will also increase. So if you kind of think about a balloon, this is a bad example, but it's the only one that we can kind of give an understanding about what we're talking about. If you think about a balloon in your hand, as you push into the balloon, the further you push into the balloon, the harder it's going to be to continue to push into the balloon, and then at some point it's going to pop. The tissue itself is going to give, it's going to fail. So this is very similar to time to contact, where there is a collision point, a point of failure. And we have based our distance to break off of time to contact. It's analogous. But this is a haptic invariant that we're trying to see if we could actually train these surgeons who have been mostly trained by visual training, instead train them to use this haptic invariant to try to help them to not cause injuries to tissues that they're coming into contact with within the body. So distance to break is just as the distance or the displacement into the tissue increases, that force will also increase until it hits a point where further force being applied will cause the tissue to fail. So we have a group of wonderful engineers that have built this haptic simulator for us. And basically what it is right here is a laparoscopic tool that we have modified and attached to a motor down here. As the participant applies force into the surgical simulator, whatever tissue we've rendered, the motor will then register force back, and that way they have this force rendering of this tissue. So we developed some materials, and the way we did them is we actually developed them based off of actual soft tissue research that's been done. And for our experimental purposes, we render them in two types of breaks. They have the true break and the maintain break. The true break is what you would actually feel if you were to break a tissue. The force value will go from the point of break all the way down to 0 newtons within that split second. So if you follow the little orange dot right here, it's going to travel up the curve, and then once it hits the breaking point, it travels all the way down to 0. So it actually has that give. The maintain break we developed so that we could do training as well as testing and not actually give them that abrupt feedback of the force value dropping all the way down to 0. So for these profiles, they actually just maintained, it's not working, they maintain whenever it was at that breaking point force value, it just maintained that force. So if you follow the orange dot again, they would travel up the curve and then follow that force value until they didn't have any more room on the simulator to actually push into. For our training sessions, for the first two that I'm going to talk about, we had this visual feedback, and the way it worked is we just put it up on the screen and we asked the people to move their red dynamic bar over to the blue bar that indicated the break point, like so. We also asked them that while they were doing this, to actually be paying more attention to what was happening haptically than visually. So the first two experiments had a 4-phase layout. We had a pre-test, a feedback test, post-test, and transfer of training. For the pre-test, feedback, and post-test, we used those maintained brakes, braking profiles. For our feedback, we had the visual feedback, and we only did a subset of materials. This is just so that we can make sure that during our post-test, when we saw an increase in everything, it was not due to actually training them on all the materials, but actually training them to be more receptive of that DTB invariant. So our first experiment, we just cared about, can subjects detect DTB, and can DTB be improved through this calibration training? And we found that. We found that observers were able to perceive DTB and that they were actually having to use the higher order relationship, not just distance or force values. We also found a large increase of about 18%, maybe 16% of increase in our R-squares through the calibration training from pre-test to post-test. So one of the issues is, after we found this, was where do we go from here? Well, there's a lot of variance within the environment that these surgeons are having to work in, one of which is trocar friction. What a trocar is this little thing right here in red, and it actually is inserted into the body, and it's what the tool actually goes through. This tool, the trocar, is what keeps the body inflated of the gas that they pump into it, and it's just to kind of help to maintain that stable environment within the body. The problem with it is different trocars equal different types of force values. Friction values. So the type of trocar can change the friction, the type of lubrication on the trocar can change the friction, as well as the amount of gas in the body cavity. So, similar to Chris's rod wielding experiments, we just wanted to be able to see if the participants were able to attune to the mechanical invariant, this DTB invariant, even when this other enforced friction is involved. So for this experiment, we had 4 primary materials. These 4 primary materials were rendered in 3 different friction capacities: no friction, low friction, and high friction. They were also done in the maintain brake and braking profiles. So as you can see here, there's no friction, low friction, and high friction in both maintained and true brake. So for the findings, we're just going to look at the pre-test and post-test for this one. And as you can see, the pre-test, there's some linearity right here, but it's not that great. For the post-test, you actually see it did help. The training feedback did help on this. And what was really interesting for us is we thought that friction might actually harm the individual, because that's what the previous research has shown. But actually, our blue line is the no friction. And as you can see, it's actually really high, and the black line is perfect performance. So people were much worse at perceiving this distance to brake in that no friction compared to the low friction and the high friction. So this, of course, made us wonder if there is an optimal friction level that we can be applying for these surgeons. And we have not done anything past this point for this. But the next thing, and something that I brought last year to the national one, was our true braking profiles that we used at the end of that transfer of training to be more real world. We had a real increase in our R-squared values. And someone told us, and in retrospect, looking back, it's like, well, no duh. We were actually giving them more training using this haptic braking point. So we decided to change our methods. We used our true braking profiles for our training phase and our maintain braking profiles for our testing phase. This reduction in time allowed us to get more of an understanding of how participants were doing in such a quick turnaround type thing. We also changed the visual feedback a little bit. Instead of giving them the visual feedback while they were training, we actually made them make their initial estimate, Then we gave them the graphic. We asked them to match the red line over the blue line, go ahead and break that material, return to start, and break it again. The biggest thing for this is that second time that they broke the material, they got the entire property profile for those materials. Another thing that we changed is we completely changed the materials from training to testing. Because if this variable is true and holds the form that we expect it does, they would be able to be trained on these materials that are all completely different, and it would be able to be transferred to these materials. So for this experiment, we had all different profiles for our training phase, and then we had these non-linear profiles that have the DTB invariant. Also within the body are compliant materials that have a linear profile. These are things such as ligaments, but we can think of them as rubber bands. And these are these linear profiles that we put in. We estimated that people would not be able to perceive the breakpoint at all for this, and that they would continue to go past it. What we found was actually quite different. We found that just as we've seen in the past, our nonlinear ones follow the line that they're supposed to be following. Everyone was able to detect that breaking point for those nonlinear profiles that have the DTB invariant. Now our linear profiles, material 8 and material 9, are all supposed to be up where this dot is, yet they are not. And we expected for them to even be higher, up here. What was happening is people were not able to even get past to the point of breaking point for these. They kept stopping at a lower force value for these. So this got us wondering about if there was potentially something happening in these profiles because they did not, number one, they didn't have the DTB invariant, but also that they did not, that there could be something happening with our force value, that there is a high force level that people are just not comfortable going past. So some other conditions that we've been testing, we tested pulling. So all of these other ones have been probing into the machine. We tested pulling, as in pulling back, and participants were also able to complete a pulling task. We tested surgeons. Surgeons, surprisingly, we expected them to be much better. They were just as good as our novices. In fact, our novices and our surgeons had no differences between them. And our novices are undergrad students, so we were really happy about that. Much cheaper. Our last one that we just did, and I presented in the poster session, we did some different types of training. And we're actually, we were happy that we found that all of them did help in training this DTB invariant to be more salient to the users. But what was interesting is the haptics only profiles were what really helped people really attune to that invariant. So Dr. Turvey asked me this yesterday during the poster presentation. So is this done now? No. We have a lot more that we want to do. And in fact, we're going back and looking at the previous work that we've done and reanalyzing it using multi-level modeling, which some people have been describing in previous presentations. And the reason that we want to do that is we don't want to be changing our data. We want to take the raw data and analyze it as is, because we feel like we'll get a better understanding of how people are using this invariant through the use of the raw data over these means that we've been using. So that's it for me. Any questions?